Hello everyone, today I'm going to present you the topic of the derivatives and let's dive into it. So first of all, I'm going to use first Miro, secondly Google Docs, then ChatGPT, and lastly Desmos. And actually, let's start with the definition of the derivatives. So first I'm going to use Google Docs, so what I wrote here. So derivative is the instantaneous rate of change of a differentiable function at a given point. You might ask what means differentiable. Differentiable means that function at any given point has a derivative. So of course, obviously, we can find the derivative in the differentiable function. All right. So then what we have is that a derivative is described as either the rate of change of a function, so I would add the instantaneous rate of a change of a function at a given point, or second definition, the slope of a tangent line at a particular point on a function. You might ask, what is the tangent line? And here's this image. So as you can see, we have the secant line and we have a tangent line. So the secant line is a straight line joining 2 points on a function, while the tangent line is the line which has just kind of 1 point, but it's like it represents the actual derivative, like so to find the derivative we need to have a tangent line. And what is the derivative is the slope of this tangent line. So basically we cannot say that the derivative is the same as a tangent line, because the tangent line is the line, but we can say that the derivative is the slope of this tangent line. So the slope of this line, okay? And this is basically what is described here. So the derivative is not the same thing as a tangent line. Instead, the derivative is a tool for measuring the slope of the tangent line at any particular point on a function, just like a clock measures time throughout the day. This is just a few examples what is actually the derivative is. So the second very important, now we got into the definition of the derivatives. Now let's dive into how we can build the derivative, how can we construct the derivative, and how actually all this work. So I'm going to use desmos.com and /calculator. Okay, and now we have our Desmos. Let's make some default settings. So we go into the tools. Wow, it's gonna be a B. Anyways, we go into here. So first, I'd like to use reverse contrast. Then secondly, let's label X and Y axes. So this is the X, and then secondly, this is the Y, just for the sake of simplicity. So now it works okay. First, I want to create a parabolic function. So the parabolic function can be described as f of x is equal to x at the power of 2. And this is our parabolic function, or just parabola. So I want to zoom a bit so we can see a bit more. I'd like to see a bit more. Let's let's stop here. So as you can see, we have 0.2, 0.1, 0.2, 0.3, and so on and so on. This is our parabolic function. I think you are all familiar. Okay, you are all familiar with the parabolic function. The question is, what about if I am willing to find the derivative at the point 0.2? So how can I do this? This is our main question here. So let's first build let's get into here, build a secant line. And by the way, I forgot to use ChatGPT, so I was willing to use it for the sake of explaining you that this is actually what derivative is. So I put into the ChatGPT, is this precisely correct, like my definition of the derivative? And it says, yes, your statement is correct. In calculus, the derivative of a function at a specific point represents the instantaneous rate of change of the function at that point. You can read it so on, but I'm going to dive into the Desmos again. So first, I want to make a second line. So let's make it. We need to choose 2 points. In Desmos, how we can do this is to just use the parentheses. Use the brackets. And into these brackets put a point. Like for example, if I want to use point 0.2 and the f of x of 0.2, what I'm about to do is to put 0.2 as an x. So the first parameter is x always, and the second parameter is going to be f of x, which is f of 0.2, f of 0.2, and as you can see, we get a point right here. This point, like placed. So and we need the second one. So the same thing we can apply. But what I wanna do is this. I wanna create the variable which is going to be equal to I'll call it x, x1, x and 1 in the subscript. So x subscript 1 is equal to for example 0.2. And the difference you will see right now. So I want to do the same things. First I want to pass x, secondly I want to pass f of x, and we get at this. And as you can see, it's a bit different from what we've got at first. If I'm trying to drag this, I can't. But what about this one? So as you can see, this one I can drag. So this is the slight difference between the variable and between the constant. Of course, this variable is a constant, but this constant I cannot change. Well, constant itself represents the concept of non-changeable constant, like number. But yeah, this is actually the variable. This is the constant. That would be right to say. So variable can change, okay? So, and this is the difference. So I created the variable to change it a bit. So let's delete the first one, and now we know how to define the variable and then use this variable to show it on the graph. The same thing, I want to create a second point. X subscript 2 is equal to 0.6, for example. I want to drag it a little bit higher, and then x2, which is x subscript 2, f of x2, and here we are. So we have the second point right here. We are almost done with the second line. So the last thing what we need to do is to draw this second line, and to do this is we just simply need to put it here together. So now it becomes unchangeable, but just I want to show you this for the sake of simplicity. Then I'll put it back, and we've created our second line. So you just a bit hold this, and then this model appears, and you just switch here to off, to on this line. So we have this line right now, so we can change the style and change the thickness of the line. Yeah. So and this is our second line. Okay. So we've created the second line, and this is basically so we now know how to create the second line, but we want to see how from the second line we can create the actual derivative. So to make this happen, I want to put this back. So you got it, that this is the second line, because I want to have the possibility to change this. So, but now this here's the second line. We just we'll do it a little bit later, okay? So now this is pretty much and I'm glad how it works. Now for the sake of simplicity, I want to create the corresponding lines to the x axis and to the y axis for both of these points. So the question is how to make it, and we're kind of say hello to Desmos. So because this is the great tool, I want to create the folder, and this folder I want to call x1. So in folder x1, what I want to do is to first put this here, not inside the folder, then create a new one which I'll put inside the folder. As you can see here is this line which says that this field is inside the folder, and I want to create by axis x, so it's going to be 0, so it's going to be here, and for y I want to make f of x1. So to make this, we just write f of x1 is here. So as you can see, I got this point here, and this is pretty much well. So and the reason why we did it is because I need to draw the line between them, but I can do it explicitly. I need to write a bit more. So to do this, I want to create the second one, which will represent the same point, just the same point, just for the sake of simplicity. Again, I put x1, which is, I'll just copy paste this, but I'll write it x1 and then f x1, and here we are. So as you can see, we have 2 points right now here, and if I'll move one of them, this 2 also moves because they dependent of the x1. So while I change x1, it changes as well. So let's put it back. And now to draw the line, again, I hold it, please hold. Okay, I hold it and then draw the line. Okay, so first I want to make this line dash line, and secondly the thickness of line is going to be 1, and the opacity of line is going to be 1 as well. And I want to use the blue color for this, and as well for this I want to use the blue color. Okay, so so we have 2 blue colors. Then to draw it for the x, we will use a bit different one, and I think you already guess what we will use. So you can go ahead and draw this, but I'll start. First, we're not anymore interested in x0 because it's here. We're interested at x 0.2, which is just x1. Okay, so then we're interested at y is equal to 0, so it will draw our dot here. So to do this, just 0. Okay, so we got it here, and I like it. So and then what we need to do is just basically draw absolutely the same. Right now I'll just copy this. So we got it here. So to draw the line, again, I hold this. I make it blue first, then I do the lines, then I do opacity 1 and the thickness 1, and then dash line. Okay, so we got our dash line and opacity and whatsoever. So okay, now I'm going to close this, and we're going to do the same things with the second one. And the reason why we're so precisely trying to why I'm so precisely trying to explain you this is because it's very important to know how works Desmos, and it's very important how did I get all of that. So if I would just start the video with all of this graph, you might say like, well, here's something fancy, I don't want to get into this. So I explain everything what I do for you. So then let's create the second folder. So the second folder will be called x2, and now I'll just do absolutely the same things. So I'm going to put it into the folder. Okay, we put it into the folder. A bit more fields, so to have some space. So now we will create for this, and for this one I want to have it be the green. Okay, so now we have the green one. So to create this, we're going to use the same thing. So first for the x, I'm going to say that this is a 0, and for the y it's just going to be f of x2. Okay, then I'm just going to copy this, just the same thing as we did before. So we got these 2 points. Now we need to connect them. Again, hold line and do absolutely the same thing. I don't want to describe it anymore because I'm a bit I'm a bit tired of it. And by the way, we can do it like the crosses and so on, but I'll use the dots. Now let's copy this. I'll just use it for, change it for the x. So for the x, I'm going to put x2, and for the f of x, just 0. Then the same things apply. Here, 1, 1 dashed. Okay. Let's put it into the folder. Now we got our pretty much good representation, so I'll just close the folder here. Now everything is simple, right? So now you can understand what I did actually. So the question right now here is, how do we actually draw the line between these 2 points? So how can we create a function which will fit these 2 points exactly? To answer this, we need to use the I'll show it to you. So let's first create the function y is equal to x, and y here represents f of x. Okay, I don't want to create the new f of x because we already created f of x, so it is basically the same thing. So you just need to know this. I wanna make it a green one. Okay, and the thickness of this line is going to be, why don't I have the thickness of this line? Oh yeah, I have. So 1 and 1 as well. Okay, so here we are, and the question is, how do we in the best way fit this? So I can make 2, and probably 2 is not correct, 0.5, and a bit probably 4, no, 6. Oh yeah, now we fit this one, but we don't fit this one. Probably we need to just add some values, which is subtraction. And somehow it doesn't work well because I need always change them, and it doesn't work at all. Like probably 1.2. Okay, now we fit this, but what about if I'll change the points? So like from 0.2, I want to change the point, and as you can see, I changed it to 0.1, and our line didn't change. So this is not the best way how we can do this. And yeah, this is basically the reason why this approach doesn't work. So now I need to use our mirror or our board to explain you how can we find slope and the y-intercept for this function, so that it would always follow our dots. So and by the way, for the dots, it's too this range is too big, so I want to create the step which is going to be 0.001, and from it's going to be from 1 to 0. So now let's apply this, and as you can see now, if I'll move it, it's a bit slider, I mean much more slider. So now we can move it pretty much well. So what was before is this is not slide at all. So what I want to do is the same things with this one. Now what we do, we're actually changing the step. So if I'll move the slider, the step of the slider is going to be 0.01, so which is pretty precise step. So and the range is from 0 to 1, which is going to be till here. So I cannot move the slider ahead of bounds of this. Oh no, okay, it's here, it's still here. So let's apply, and now it's very slide. So as you can see, I can't go out of the bound of 1. Of course I can make it 2, but just so that you may know what is the range. So now we need to solve this problem. How can we fit this line? And to solve this, we are going to use mirror right now. Okay, so let's start. And I'm going to say that, yeah, let's use text at first. We have y1, which is equal to kx1 plus b. So the second line is going to be y2 is equal kx2 plus b. So what is this actually? So let's actually separate it a bit to make it simple. A bit separate. Okay, so now let's put it here. Okay, works fine. Yeah, just here. So what is this? This is basically two equations. or in other words two functions. So to show this is basically it. Let's actually delete this. I'm going to say this y is equal to some k value x plus b, and this is going to be y1, all of them. Okay, we didn't get anything because y1 doesn't work. Nope. What's the problem here? Oh, of course, our bias is 1. It's out of the boundary somewhere here. Yeah. So let's make a bias 1 right now. A bias or the y-intercept, whatever you like to use. And we need to create the second one. And for the second one, we don't need to create these variables again because they're already defined. So just x, kx plus b. So, and this line works as well. And let's make it purple. So if I'll turn off this, I see this. And basically we have right now two functions over each other. So purple over the green. So green and then purple goes. And they're basically the same. So if they're the same, we can get out of this function I'll just show it to you. So we can get b from this function. So, and how to do this is this. We just say that we have this, and I want to say that b is equal to. So now, if I wanna get just b, what b is equal to, I wanna say that b. I wanna say that I wanna subtract key x2 from here and from here, so from the both sides, and this will be correct. So from the both sides, I will subtract key x2. So what happens is that first I say b is equal to, let's make it 3 here. No, delete the dots. B is equal to first y2 minus this, because I'm subtracting it from both sides, of course, y2 again. So y2, then subtraction. Okay, we subtract, then equal to this, and then equal to plus b, and then subtract. No, wait. Plus b, and then subtract this. So this one will be cancelled. So we will get just b here. So if we will cancel them, cancel, because my 1 minus 1 is 0. So here's the same things. We got this formula, and to make it in other words is just b. I'll just switch the sides, is equal to y2 minus kx and 2. Okay. So now we got what b actually is. So now if I will put inside instead of this b this will work fine as well. So if I'll say for y1 is equal to kx1 plus b, and instead of b I will use this will work perfectly the same way. It might seem to be hard, but it's not. So we just explored what b actually is, and if you don't believe me, let's check this out. So we have these two functions, and what I basically said is that from y2 we can make b, so, and b is equal to let me actually, and b is equal to y2 minus key x2. Let's check this out. So it says key x minus, what is there, minus y2, and what is our y2 is this. So minus y2, and then plus y2, of course, plus y2, and then minus k x1. Okay, here we are, and something went wrong a bit. Oh, of course, because we used k x1. If I'll use x, as you can see, we get the same line, absolutely the same. So if I'll move this, we have this line, and if I'll put it back, we have it. So as you can see, this is absolutely the same as this, and this means that our equation works fine. So now The reason why we can do this, because b and k are the constants. If they are the constants and the same, we can explore b from the y2. So, and this will work perfectly fine. Alright, now we have this. And the question is, what about if I want to find k, like our slope? So first of all, let's find our slope. What is our slope? So to make this, first what I want to do is to put plus y2 at the end. So this is what I can do. y1 is equal to kx1, then minus kx2, and then plus y2. Okay, so this is the same as this. I just switched some elements inside. Now, as you can see, we have the same axis. I mean, we have the same k here, but the different axis. So what I can do here is this. I can say like y1 is equal to k, and then brackets. So, and inside the brackets x1 minus x2. You may say, those of you who are not familiar with this, how does this actually works, and the answer is that if I multiply k on x1 and minus x2, I'll get absolutely the same. So I'll get kx1 minus kx2, so which works fine, and then I just plus y2. So now the question is, I need to find this k. So now we got just 1k. So to do this, in order to do this, we go further. And now we say that I want to first subtract this from this side and from this side. Sorry. So what I'll get is y1 minus y2, which is equal to k, the same thing, x1 minus x2, and then plus y2 and minus y2. So this cancels. So I can just cancel this, because y1 minus y2 minus y2 is just 0 or nothing. So I'll just delete this. Then we already pretty much far away from. I mean, we're closer. We're getting closer to our solution. So now what I'm about to do is divide both parts on x1 minus x2. So to do this, it will be something like that. I can make the brackets here. It's not. I mean, it's allowed. So, and then divide. This is the dividing. Divide it on our x1 minus x2. Okay, and then this is equal to k x1 minus x2, and then divided by x1 and minus x2. So this 2 cancels, this one and this one, so we got just k, and here it remains. So to cancel this, we just do this. And as you can see right now, I'll just switch again the places. So I'll say k is equal to this. Let me just copy this. Okay, so we got our k. Let's actually get it into here. So our k is equal to this. First we found our first we found our bias, or b, or y-intercept, which is equal to this. So now we have 2 of this, and it means that we can find now how our slope will look like. So let's apply this. So first I want to find our slope. So our k is the slope, or in other words, k can be m. I mean, usually it's m. I just used k. So now we're gonna make it. So let's delete these functions, because they don't need anymore. Just one of them is needed. Let's create y is equal to x. Okay, we've created a new function, and now I want to say what is our k or m. Let's use in the context of Desmos m, which is the same as k here. So k, and I'm going to say that what is our actually y1 and y2. So our y1 and our y2 is this. This is our y2, f of x of 2, and our y1 is f of x1. So I will say that let's make first, what is that? First, f of x1 minus f of x2, and this is our y's, okay? So this is y1, this is y2, and then I'm going to say that this is minus x1 minus x2. Okay, and now we get our slope. Here we are. So now we have the simple slope, which is 0.45. This slope is 1. No, not 0.45, of course. This is slope 1 right now. If we will go here, and I say that it's equal to 1, this is slope 1, this is equal to, this is slope 2. So basically 1 is here before of it. So now let's create our slope, and 1, 2, 3, go. Our slope is created. And as you can see, this slope it's exactly what this slope was here before. So we got our slope first. Then what about our b? So our our bias. So for our y-intercept plus 1, for example, no, plus 0.1, we got here because this is 0.1 for y-axis. So what we're about to do exactly what we just got from here. So first I want to make plus y2. What is our y2? Our y2 is f of x2. So let's make f of x2. Okay, and now as you can see, we're on this line pretty much well. So the second is that we're going to say that we're going to subtract kx2. Okay, so let's make it. So what is our k first? Our k is this m, which is slope. So I say subtraction or minus m first, the slope, and then secondly what we are going to subtract is our k multiplied by x2. What is our x2? Our x2 is this, or simply this, our x2. So and do this, 1, 2, 3, go, and we got it. Here we are. Okay, this is pretty much well, and this is precisely precise, yeah, tautology. So I make it a little bit thicker, yeah. So and let's make it green. So you can do whatever you want. Oh no, I'd like to see it as blue. Yeah, pretty much nice. So now if I will use my slider, as you can see, our slope is changing. I mean, our function changes. So this is what I was exactly about to get. All right, so we're almost done with our derivatives. So how can we actually find the derivative? So what is our derivative actually? Is our slope of the tangent line. So you might have a question. So how can we find it? Okay, let's find it. So what basically derivative is an instantaneous change, as we saw here, is the instantaneous rate of change of different functions at a given point. So I wanna choose a given point. So what will be our given point? Let's use it as 0.4. So our given point will be 0.4. You might ask, why do I use x1? Why didn't I use x2? You can use x2. So whatever you'd like, you can use. But now we need just one given point, which is going to be 0.4. So what our derivative is this. I will slightly go. You see, now I have a secant line, right? So this is the secant line without extending one. So now I want to make my secant lines slightly smaller, lower, until I will get into this point. And if I'll get right into this point, it vanished. So why did it vanish? And the answer is it vanished because we have exactly the same, and there is no derivative if I have the same points. So the condition of the derivative is to have a limit. So what means limit? It means that it's extremely instantaneously close to the point. So it's not exactly the point as here, 0.4, 0.4. It's absolutely near, like infinitely near to our point. So what it means is this. Just myriads of this O, and then at the end 1. And it didn't work. So why it didn't work? Okay, probably Desmos has a has a limit for this. Probably, yeah. Just say, let's say it's infinitely close. So and now we have this line. Here we are. So this is infinitely close to our point, and this line we call a tangent line, and the slope of this line we call a derivative. So how can we know the slope of our line? The slope of our line is exactly here. So this is the slope of our line, 0.8, 0.8049, whatever. So now we got our derivative. So you wanna, if you want a more notation, let's dive right now. But now you already know what is our derivative. So we had a secant line, and from the secant line we got into the tangent line, and this tangent line infinitely close, 2 points which are infinitely close to each other, and we don't call them anymore 2 points. We call just 1 point. So at a given point, you might say like, well, if definition is like at a given point, why do we have 2? But the second 1 point, which is x2, is infinitely close to the first one. It means that it's like almost exactly 1 point. One given point at a function. So yeah, and this is how it works. So now let's dive a bit into the notation and how do we like write it in the math, fancy math, and so whatsoever. So I want to say like I want to have 0.8 and 0.4. Let's make it 0.8. Okay, so we have 0.4 and 0.8, and the slope of this is 1.2, and of course it's not a derivative yet because this is just the slope of the secant line. Okay, so let's dive into notation. So I'm going to open x1 first. So and I want to say that for okay, so I want to create a new one. Let's put it into here. Okay. I wanna take this point here. So this point here is, I believe, not okay. I believe that, yeah, this is it. So I create a new one just over the previous one, and I want to label it. So the label will be f of x. Okay. So this is our f of x. So for that one, let's make it actually. Get it here and into here. So for that one or this one, I'm going to say that this is our x. So x1 and f of x1. Okay. Let's change the. I don't like it. Okay. So now we have this. Pretty much good. Pretty much good. Well, I don't want to drag it, but anyways, can I do it not draggable? Yeah. Okay. It's not draggable anymore. So now this is our f of x1 and this is our x1, which is correct, right? So the same thing I wanna do for them, and as you can see, while I'll move them, they goes with it. So for the x2, I'm going to do the same things. Let's create some more fields. First one, and then the second one. I think I can copy them, but I don't want. So for this one first. So we create for this one first label, and this is our f of x2, and let's call it for now like this, f of x2, and make it this is green, right? So let's make it green, and let's actually change the position to here. Okay, so now it's good. So yeah, we are here, and then for the x2, I want to make it first non-draggable. So non-draggable, and then the green one, and the position, not yet position because we didn't make a label. So to make a label is going to be x2, right? So and change position to here, so or to here. Oh yeah, here. Yeah, okay, perfectly. Perfecto, as in Spanish. Okay, so now we have f of x1, x1, x2, and f of x2. So now you might say, so why did we do this? Because this is extremely easy to understand that this is f of x2 and this is x2. So, but what actually our x2 is? And this is actually the f of x1. Take this change in the y-axis, takes this change plus h. We will say this distance between them is h. So will I be correct if I would say, no, let's make it here. Will I be correct if I'll say for x2, where's the x2? If I'll say that f of x2 is exactly what is f x1, a bit here, x1 plus h, considering that this h is this distance between them, okay? And I'll be correct, because f of x2 is exactly what I wrote here, f of x1 plus h plus the distance between them. So if I'm correct in the statement, let's leave this without f of x2. No, let's, for the sake of simplicity, I'll leave it. What about the x2? So this exactly the same things. I just say that x2 is equal to x1 plus h plus this distance between them. Okay, so let's make it. So x2 is exactly is x1 plus the distance between them, x1 plus h. Okay. So what is our tangent line again? Our tangent line is just rise over run, if you would like to call this. So this over this. So rise over run. Well, how can I explain it simply? Well, I know almost everyone of you is familiar with rise over run. So we are going to divide this on this, and we will get our slope. So as we did here, just look at here. What is our slope? As this, what we exactly got from our formula. So what about if I'll change this on our f of x1 plus h and x1 minus x1 plus h. So let's make it. You see, we got this formula, and now I want to use my pencil. So I want to say that our so how do we define the derivative? Is this f and then dash here, this dash, and then x of x. So this is how we say that this is a derivative of our function. So our function is basically f of x, and this dash represents the derivative. And of course there is different representations of the derivatives, like d over dx. This is another one representation of the derivative, but we're not gonna dive into the types of how can we denote the derivative. This is just simple one. So f of x, f dash of x, and then f of x. So we actually don't need this f of x. We are talking about the derivative right now. So again, what is the derivative? The derivative is the slope. So basically this f of x is our slope of our tangent line. This is basically this m. This is basically the k, okay, k or m, whatever. So now we can understand how it works. So I'm going to just rewrite this into our definition of the derivative. So our derivative is equal to first f of x, f of x1 minus f of x. Basically, the proper way to do this is to say that f of x2 minus f of x1, because f of x2 is greater than f of x1. But how we've made it from the second one, not from the first one, and this is the reason why we a bit changed them. So let's say, for the sake of simplicity, that this is actually it. So let me find the eraser. Basically will be the same things, because we just got the minus and it's going to be positive, but we don't want to do this, so we do it positive at first. I did the same things, right? x2 and x1. So then over, so our rise, so this actually is our rise, so this distance between this and this, so here, right? Yeah, and basically, of course, yeah, so here's one problem. I said that oh, no problem at all. So this is our rise, okay? So this is our rise, which is here, but we find it like this. So this is our rise. So as you can see, our rise is f of x2 minus f of x1. So we get this h actually from here. So this is our rise, and our run is this. So this distance, or we can represent it here a bit lower from our point. So it's basically x2 minus x1, and we get this h. Okay, because again, x1 minus x1 is going to result h. So this distance between them. Okay, that's pretty much cool. So we say that x2 in this case, okay, okay, wait, x2 minus x1. So there is no difference. So we will say fx1 minus fx2 and x1 minus x2. We'll just get the negative numbers for both of them, but at the end, negative over negative is gonna result positive. Okay, so this is the reason why I just want to switch them, so to get positive right away after division. So okay, and what this actually is this is equal to, now this I want to change into where is it, into fx. Oh yeah, of course, here's the mistake. I've made a mistake. This plus h is not outside of this function, it's inside this function. So and the reason why is it signed, because if it will be outside the function, our function will result incorrectly somewhere out there, and when it's inside the function, which is exactly for our point here, 0.8, it's exactly here, so it's going to be inside the function, and I've made it incorrectly here, so sorry for that. So now this is correct, so we're going to rewrite this f of x1 plus h. So we're going to say f of x1 plus h. Okay, so this is basically the same as f of x2, and then minus f of x1. Okay, okay, and then over, so rise, this is the rise, over run. So what is our run? Our run, what is x2? x2, now here I said it correctly, x2 is equal to x1 plus h. So I want to say just instead of x2, x1 plus h, x1 plus h, and then what's then minus x1, minus x1. So what happens here is that this cancels too, so both of this cancels, and we get this h just, and we basically say that our derivative is just f, and this doesn't cancel because of course inside this function is h, and this is not basically the same thing. So fx1 plus h, okay, and then minus f x1, and then over our h, because h is positive. So now what is our derivative? All right, our derivative is this. So this is the formula of the derivative, which you will see in all the notations, all the books, all the classes, maths, whatever. So so we got our derivative. So this is our derivative, and what basically is derivative is that what we got there. And so the last thing which I need to mention is that this is not basically a derivative at all. So this was for the sake that you may understand that this is not a derivative. Okay, and the reason why it's not a derivative, because we don't have this limit. Let's actually put this limit. Okay, so I wanna oh my, what is this? I wanna put it, no please take all of that. Okay, so I wanna put it here and say that take this equals away from me. Okay, I'm gonna say that here's gonna be, no, not the text, limit, which says that our h approaches to 0. So you might say, why h approaches to 0? Again, let me show it to you again. This approaches our 0.4 until it will get into almost the infinite closeness to them. So if I would say 0.4, I don't have just this tangent line. So I need to make a limit. So it's not exactly 0.4, but it's infinitely close to 0.4. So this is the instantaneous change. Infinitely, like millions of myriads zeros and then 1, and we get our slope. So this is basically the tangent line again. This is the tangent line, and the slope of the tangent line is our derivative, and this approaches 0, like 0, 0, 0. It will approach 0 infinitely close, and this is what actually is the limit. Whew. So now you know what is the derivative. So from here, you might calculate any derivative which you want, and you might say, well, how can I calculate this? Make some examples of the derivative. Well, if you want it, let's make it. Let's find the derivative of our parabola. So what I say by that is that I don't want to find the derivative of the given point. I want to find the whole derivative of the parabola. So for any parabola, I want to find the derivative, what it will be like. Okay, so not for the given point, but for every point of the for every point of the parabola, I want to know what is the derivative of it. Okay, now let's go here again, and here's actually our formula of parabola. So okay, I'm a bit thirsty, so let's no, please get out of here. So let's say, what is our parabola? So our parabola is this. First of all, limit. So limit, where it's a bit hard with the touchpad. Like draw here something. H approaches to 0. This is our limit. Our limit, and then over. So what is our f of x1 plus h? It's just simply x1 plus, and we can actually remove this one because we don't have any other x here, so just x plus h in squared, because what is our parabola function? It's squared, right? So f of x plus h is going to be x plus h in the power of 2. So and then minus this is going to be just x in the power of 2, then over h. So our h approaches to 0. Then we go further, and we say that we just want to explode this x plus h in the brackets, and then another bracket. So this is basically what is the exponentiation. It's just multiplying by this number. So we got here, so then minus x2 as well. Now I want to explode this again, so I want to open these brackets. So x multiplied by x is going to be x squared. So first I get x squared. This is just like that. It goes here. So a bit curved line. So okay, x multiplied by x is going to be x2. Then I want to multiply it by this. So it's going to be plus xh. But if I will then continue, like multiply by hx, this is going to be the same, xh. So I'll just say 2xh. Okay, 2xh. Because you see, so we got xh from here, and from here hx, and I can just switch them to get xh, so it will be just 2xh. And then finally plus h squared, so plus h squared. and then minus x squared and over h. So now what cancels from here? So first cancels this and cancels this, and we go farther. We say that now we have 2x h. Oh no, pretty much bad h. Probably I need to change it to make it a bit thicker, like this. Yeah, much more better. So now we have 2x h minus plus h squared. So this 2x squared cancelled, and over h. So now what I can do is to take it out of the brackets. So now to say that I have h, and of course I forgot to put everywhere limit. So here shall be the limit before, and here shall be the limit before, and here shall be the limit. So limit where don't forget about the limit. So after every equal symbol you need to have a limit. So limit where h, it's so hard to use a touchpad for the drawing, h approaches 0. Okay, so the limit before this, and before this as well. So let me raise this for a while. So limit where h approaches to 0 and over. So now I'm going to put h out of them. So we have 2 x. We take out h out of it, plus h. Okay. And then over h. So if I'll multiply h by 2x and by h, I'll get absolutely the same one, 2xh plus h squared. And what I can do is now cancel them, right? Because this is multiplication between them, so I can just cancel them. So I cancel 2h, and what I get is just simply limit. Don't forget about the limit. It's always shall be with you. Limit approaches to 0, where is 2x plus h. And what we may say is that h approaches to 0, and this is basically almost 0, so we can just delete h and say that this is basically 0 and this is just 2x. So the derivative of the parabolic function is 2x. And to check this out, I want to draw lastly, and this video is done, that the derivative of the parabolic function is just simply y is equal to 2. I just recapped my video, and I think this explanation will be a bit better. So the derivative of the parabolic function is f of x. Let's make it x1. No, let's make it actually g of x is equal to f and dash, as you remember, of x. So this is the derivative of the parabolic function, and you might ask, so why is this the derivative? Because derivative is the instantaneous slope of change, the given point, and you're right, because this is the derivative for every point on the sigmoid function. We just draw how it will be look like. So to make a simple example, we actually can look at this. So you can just see that right now we have 0.7999, which is just 0.8. So, and if we will go a bit higher, we will see that for our 0.4 the derivative is 0.8, as you can see. So this is basically it. So we got the correct derivative because it's almost 0.8. And yeah, to use a bit another example, what I want to do is I want to set up it on 0.5. So let's find 0.5. Okay, right now it's 0.501, so just 0.5, and here somewhere 0.2. Okay, so now we're interested in finding derivative, the derivative for 0.5. So to check if this line works out for any given point for the parabola function, I want to do absolutely the same things. I want to make it infinitely close to 0.5. So, and as I do this, okay, I almost infinitely close, and then I'll just use my hands to make it. Okay, now I'm infinitely close, and this is our derivative, so it says our derivative is 1.0, and if we will look at this, the derivative for 0.5 is 1, which is our derivative. So as you can see, everything works fine, and in such a way you can find the derivative of anything. Like for derivative for the x equal to 1 is just 2, and to check this out we just use the same thing. So we go to 1, which is our maximum, and we go as well here to 1, but infinitely close. So, and it says the derivative for this is 1.99999, and probably we can make it even more, so to get 2, okay, we got 2. So, and the derivative for x equal 1 is 2. So, hope this video was helpful. I'm glad that you were with me. Please consider to subscribe to my channel. Nothing more. See ya.